Right, so we're going to do problem BFH6 from the harder problem sheet. So this is a blood flow calculation. We've got a two-dimensional model of arterial blood flow in a channel. So according to the question, the channel walls are at y equals 0, like that, and y equals d up here. This is the x direction, and the fluid is moving from left to right in the positive x direction with velocity little u, which is a function of y and t. And we're given that the equation of motion is du by dt equals a cos omega t plus u y. Now, what are we asked to do? First of all, state which fluid mechanical quantity is linked with the onset of arterial disease. So that is the wall shear, as we discussed in lectures. Then we're asked to write down boundary conditions at the arterial walls. That's at y equals 0 and y equals d. So this should be the no slip condition, which states that u equals 0 at y equals 0 or d. Okay, so that's the first two bits done. Then we're asked to actually calculate the flow field by looking for a solution in the form u of y comma t is the real part of e to the I omega t times f of y, where f here is complex and I is the square root of -1. Okay, so this is exactly the same type of calculation that we did in the lectures. Let's start by substituting this form here into our PDE, which is here. I guess in order to do that, actually, it's helpful to rewrite cos omega t in terms of e to the I omega t. So let's note that cos of omega t is the real part of e to the I omega t, according to Euler's formula. E to the I omega t is cos omega t plus I sine omega t. So if we call this, say, equation star, then equation star becomes as follows. So du by dt, I need to differentiate this with respect to t. Let's leave the real part in for now. Differentiate with respect to t, I get I e to the I omega t times f on the left-hand side is equal to a times the real part of e to the I omega t plus uyy, so that's the real part of e to the I omega t times f double dash. Okay, so now let's take the real part as understood. Okay, so we're not going to write down the real part anymore, we're just going to understand implicitly that it's there. So what I've got now, if we divide through by e to the I omega t, is if is equal to a if times omega. I've forgotten the omega here, so there should be an omega there. If times omega is equal to a plus f double dash, which we could rewrite as f double dash minus I omega f is equal to minus a, if we wanted to. So this is a second order ordinary differential equation, constant coefficients. These coefficients of f and f double dash are constant. It's inhomogeneous because there's minus a. So let's look for a particular integral to knock out that minus a on the right hand side. That looks like if we choose f to be a over I omega, that's going to do it. If I substitute in f is a over I omega, I will get the left hand side equals the right hand side. Multiply top and bottom here by I, so that's minus ai over omega. So with that in mind, then let's make a new definition. Let's write f is minus ai over omega plus g of y, and we'll try and determine what g is then in that case. So we substitute back into our f equation here. The a is going to disappear now because of our particular integral. So we'll be left with g double dash minus I omega g is equal to 0. Okay, so then let's then make a new definition. Let's let sigma squared be I omega. The reason for doing that is I tidy the equation up now. So I've got g double dash minus sigma squared g is equal to naught. So if we seek a solution in the form g is e to the my, say, substitute into here, differentiate twice, I'll get m squared times e to the my. E to the my is going to be common between both terms, so that can cancel out. So I'll get m squared minus sigma squared is equal to naught. That then implies m is plus or minus sigma, so there's two possibilities. So we can form a linear combination to get the general solution. G of y is alpha e to the sigma y plus beta e to the minus sigma y. Right then, so we can continue. We can substitute f back substitute g rather back into f. Then the boundary conditions, what do they need? So here are my boundary conditions up here. U's got to be 0 at y equals 0 or d, but we've written u in this form. So if u is 0 at y equals 0 or d, that must mean f is. So f of 0 equals f of d is equal to 0. That's going to give me two equations then. Minus ai over omega plus g of 0 is equal to 0. But I've got my general form here for g, so that's minus ai over omega. Substituting y equals 0, I get plus alpha plus beta. That's got to equal 0. And so that one implies that, and this one comes down here to imply this. Minus ai over omega plus g of d is then minus ai over omega plus alpha e to the sigma d plus beta e to the minus sigma d has got to equal 0. So the aim then would be to solve these pair of simultaneous equations for alpha and beta.